Hey, so what do dipoles say in passing? Have you got a moment? Welcome! In this video, we're going to be talking about analyzing the properties of compounds and solutions. But first, if you did not get that last joke, do yourself a favor and go back to my last lesson called Investigating Chemical Compounds, where I do explain what a dipole moment is, as well as a lot of other concepts that are important as prior knowledge to understand this lesson. So go back there and do so if you need to. Now, let's talk about a number, Avogadro's number. This is a really big number. Oh my gosh, look at all these zeros. What is this number? Well, let's see if we can figure this out. This would be the hundreds, thousands, millions, billions, trillions. There's our national deficit here, at least as time of recording. Next, it will be in the quadrillions, then quintillions, and finally sextillions. So this number, Avogadro's number, would be pronounced or said 602 sextillion 200 quintillion. This is a really big number. This number is referred to as a mole, M-O-L-E. This is a mole. And instead of writing all these zeros, we put it in scientific notation. And basically the decimal point is over here right now. If we move it over 23 times, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So if we move it over here, we can just write 6.022 times 10 to the 23rd in scientific notation. So a mole is a number. This is the number, just like the word a dozen is a number. And you guys should know a dozen is the number 12. A mole is just that. It's just a number. You can, just like the number 12, or I'm sorry, the word a dozen, you can have a dozen of anything. You can have a dozen donuts, a dozen eggs, a dozen anything. Well, if you have a mole, you have 6.022 times 10 to the 23rd of something. So what is a mole used for? Well, it's useful when counting many small particles or when you're dealing with the balance in my bank account. Oh, yeah, I wish. So this number here is based off of the atomic mass on the periodic table. So the atomic mass is measured in grams per mole. That would mean for any element on the periodic table, when you look at its atomic mass, if you have this many atoms of it, that would be the mass of it. And this was determined by experiments that when we looked at carbon-12, the isotope carbon-12, they found that for it to be 12 grams, there had to be this many atoms in it. And that's the basis of where a mole comes from. So to match the atomic number, this is how many atoms are in it, and that's what a mole comes from. A mole is how much you have of something. Like a dozen is how many donuts you have. But we don't count atoms when we're doing chemistry. We might take the mass of something. That's more reasonable. We take a balance and we mass things out. But what's happening is atom for atom is what's reacting. So to get the same amount of atoms for different substances, they are different masses. In other words, a dozen feathers weighs different than a dozen bricks. Different atoms have different masses. So we have to convert mass to amount and amount to mass. So right now, let's do a practice problem of converting the amount of something to its mass. So determine the mass in grams of 5.50 moles of iron. So to do so, you have to look at your periodic table, and you should have a periodic table in front of you right now. If you don't, pause the video please and get one and verify that on your periodic table the average atomic mass for iron is 55.85. And what that means is there's 55.85 grams for a mole of iron. And now to convert 5.5 moles of iron, I'm going to do this in the method of dimensional analysis or factor label method. It means the same thing. It just, we say it two different ways for some reason. So using dimensional analysis, I set this up since I have what's in the problem here, 5.5 moles of iron. I put that, I always start my dimensional analysis with what came from the question. And then I use from the periodic table 55.85 grams per mole. I'm going to use that to cancel out units. And so I'm going to use this equivalence and I'm going to set it up for units to cancel. Since I'm starting with moles, I'm going to put the 1 mole on the bottom. And if I put the 1 mole on the bottom, what's on the top and the bottom of a fraction cancel out with each other. And so now my unit left over will be grams. The moles of iron cancel with moles of iron, and now I'm left with grams of iron. So it would be 5.50 times 55.85, and when I multiply those together, you get 307. But the reality is you actually don't get 307. Let's talk about significant figures for a moment. When we put this into a calculator, let's try that. 5.5 times 55.85. Your calculator comes out with this number, 307.175. We don't record this whole number in our answers in chemistry. The reason being is the number we started with had 3 significant figures in it, 5.50. Zeros are significant if they come after a decimal place. That's why a lot of times people would think, well, why don't we just put 5.5? This means how far we actually measured something. So we measured something out to 3 digits basically. So that means our answer when we're multiplying and dividing should also have 3 digits in the answer and not putting all these extra digits here. If this 0.1, if this would have been 0.5 or greater, we would round up. So it would be 308. But this is less than 5, so we don't round up. Okay, let's try another one. Let's determine the following. Determine the amount of moles in 32.4 grams of iron. Converting grams to moles and moles to grams is essential in chemistry. So let's try that. So we're talking about iron again, so we have to look on the periodic table and we find iron's molar mass, 55.85. So 32.4 grams. This time we're in grams. So when I set this up using dimensional analysis, I'm going to set it up opposite of the last time. I'm flipping this over. And the reason I'm flipping this over is because I'm starting with grams and I need grams to cancel out. So grams cancel out with grams. Now I've converted the grams into moles. So I would take 32.4 divided by 55.85. So you actually put it in your calculator just like this. You put the 32.4 and then this line, you can extend it over, divided by 55.85. And the units left over would be in moles. So we'd have 0.580 moles of iron. So let's try that in our calculator and we'll talk a little bit about significant figures again. So 32.4 times, 32.4 divided by 55.85 equals, and we get this gigantic number here. Now, I'm not going to write all of this in my answer. That would actually have too many significant figures. That means a very precise measurement. The original measurement only had 3 significant figures, so my answer needs 3. Zeros in front of a decimal place are not significant. They don't count, only the ones at the end. So since I don't count the first 0, I would have 0.580, and I'm going to count this last 0 here to show 3 significant figures. So your 3 significant figures are 0.580, and that's why I would do it that way. Not all things that we deal with in chemistry are just elements. Sometimes we're dealing with compounds. So for instance, instead of just dealing with iron, maybe we're dealing with rust, iron oxide. And this is iron 2 oxide, representing that the iron has a charge of 2, and you should know at this point that oxygen has a charge of 2 as well. So I mean positive 2 and negative 2. So it's a 1-to-1 ratio. Anyways, so let's convert 67.2 grams of iron 2 oxide into moles. To do so, we have to consider that it's got 2 atoms in this case here, and some things have 3 atoms or 4 atoms or billions of atoms. You have to take all the atoms into consideration when you're determining the molar mass. So the molar mass of iron 2 oxide would be, you have to have 1 iron and 1 oxygen. Again, if you had more oxygens or irons, then you would multiply these numbers by how many irons or oxygens you have. You have to add up everything in the compound. So iron has a molar mass of 55.845 grams per mole, and oxygen has a molar mass of 15.999 grams per mole. We get this is off the periodic table. We add them all up, and you get the molar mass for iron oxide as 71.844 grams. So I trust that you guys can do this part. So you just add up everything in the compound. All right, since we're starting with grams, we are going to use this number here, this molar mass, and we're going to set it up so that the grams are on the bottoms, because on dimensional analysis, I want the units to cancel out. Since I'm starting with grams, I set this up to cancel. And I set it up to cancel by putting the grams on the bottom and the 1 mole on the top. So we would take 67.2, and then we would divide it by 71.844, and our answer would be in moles. And this would be the correct answer. Let's take a look at what our calculator would say when we try this. So 67.2 divided by 71.844 equals, and again we get this another huge number. The number started with 3 significant figures here. We've got 3 in our question, and so and here I'm not rounding off to 3 because my answer isn't what's the molar mass of iron oxide. We don't round off until we get to our final answer. That's an important thing to note. So as we do this in our calculator, we get this huge number. Remember, leading zeros are not significant. Trailing zeros are. And since we have 3, I'm going to put these 3 numbers as my answer. And again, if this was not a 3, if it was a 5 or greater, then it would round this last number up. But it is less than 5, so we don't round up. So this would be the answer with 3 significant figures. All right, I'd like you to pause the video and give these ones a try. So convert 9.62 grams of methane, which is CH4, into moles, and then convert 0.0431 moles of sodium hydroxide into grams. Remember to answer with 3 significant figures here, and you're going to have to add up a carbon and 4 hydrogens for this one. This one over here also has 3 significant figures. Why? Because leading zeros don't count. Remember, leading zeros don't count. So the significance is the 4, 3, 1. And you're going to have to add up a sodium, an oxygen, and a hydrogen. So pause the video, give that a try. A solute is a substance that dissolves in a solution. So when you put something in a solution and it dissolves, that thing you put in there is called a solute. The solvent is a substance that dissolves the solute. So the solvent is what is dissolving the solute. Basically, you have more solvent than you have solute. The thing you have a lot of is the solvent, and what's being dissolved into it is called the solute. And when you do that, you create a solution. So a solution is a mixture of solute and solvent together. Isn't that annoying? They all start with SOL. Solute, solvent, solution. So let's just analyze what happens when we put Alka-Seltzer in water. When you put Alka-Seltzer in water, the Alka-Seltzer dissolves. So therefore, the solute would be the Alka-Seltzer. The solvent would be the water, and as it's dissolving, it's creating a solution. And that will help your tummy when you don't feel good. Okay, we need those terms to talk about this next point, which is called molarity. Molarity is the concentration of a solution, and it is represented in moles of the solute, and now we know what a mole is. So it's how many particles, how many atoms or molecules we have of what's being dissolved. So moles of a solute, so how many things are being dissolved in there, and per over a liter of the solution. So if you have a liter of a solution, how many moles are in it? So Something students get confused about when they're first exposed to the word molarity is the way it's used in problems and in chemistry. So molarity can be worded many different ways. So you might see it written like this, 1.5 m. That means the molarity is 1.5. It might be written as 1.5 molar. So a 1.5 molar solution means it has a molarity of 1.5. So you can see a capital M, that's the abbreviation, or it might be molar, or they might write the molarity is 1.5. So this is all the same thing. The units for molarity is represented as a capital M, and as we saw over here, per moles per liter, and a mole is represented with just MOL. I know it's not much of a abbreviation when the word is MOLE. You get to cut off the E for abbreviating it. Per liter. Also remember that it's moles of solute, what's being dissolved in the solution, and over how much of the solution you have. Please make sure that the molarity is a capital M and liters is a capital L. Moles is MOL, all lowercase. Make sure your capitals are capitalized and your lowercase is lowercase. It's very important in representing units in science. Okay, let's do a practice problem with molarity. What is the molarity of a 2.0 liter solution with 3.0 moles of HCl in it? Well, what are we solving for? We are solving for molarity, and we know that molarity is moles per liter. We also know that we have 2.0 liters of solution. And again, why is this 0 here? Because if there's a period, if there's a decimal place, zeros at the right, at the end, these are called trailing zeros, are significant. If there was no decimal place, it wouldn't be significant. So in other words, the number 20 only has one significant figure. And that goes as a denominator. We also have 3 moles of HCl, which is hydrochloric acid, by the way. That's our solute, what's being dissolved in the water. So we have 3.0 moles of HCl. We take 3 divided by 2 and you come up with 1.5. We use the whole 1.5 because we have 2 significant figures in both of the measurements in our question. If one had 2 significant figures and the other one had 3 or 4, you're going to still answer with the least amount of significant figures when you're multiplying and dividing. So if you're multiplying and dividing, you answer with the least significant figures in whatever's given in the question. In this case, they both have 2. That's why we're going to answer it with 2. And moles per liter is also molarity. So we've talked about some different types of things so far mathematically, so let's just do a quick little breakdown of what's going on. I like to use dimensional analysis so you don't have to memorize these things, but if you'd like to kind of take a look at what do you do when you're doing stuff in your notes, we'll do that as well right now. So when you're converting moles to grams, you multiply by the molar mass. You get this off the periodic table. So if you have to convert your moles into grams, multiply it by the molar mass. If you have to convert your grams to moles, you divide it by your molar mass. Let's take a look at a practice problem. If we're going to convert 125 grams of water into moles, and this is the molar mass of water, and you get this number by taking oxygen plus 2 hydrogens, or 2 hydrogens plus an oxygen. You have to add up all of that. If you do that on your periodic table, you should come up with a number around 18. So do I multiply 125 by 18, or do I take 125 and divide it by 18? Well, let's take a look here. We're converting grams into moles, so that would be right here. So that would be divided by. But if we set this up with dimensional analysis, we don't have to memorize the part on the left. We can just take a look and make sure the units cancel. So I have 125 grams of water, and I'm going to divide it by the 18 grams of water. And how do I know? Because I want the grams to cancel and I'm in moles. So you set it up to cancel. When you do that, you get 6.94 moles of water. Let's just try this, practice a little significant figure work. 125 divided by 18 equals, well, we get a really big number, and we are going to answer with 3 significant figures, and that's why we have this number here. Let's take a look at another important thing that we're dealing with when we talk about molarity. We talk about solutions. In lab, we usually measure things in milliliters. A liter is, it's a liter, you know what a liter of water is. We usually measure things in milliliters in our chemistry lab. So converting liters to milliliters, you would multiply by 1,000. So there's 1,000 milliliters in a liter. So if you have to convert the liters to milliliters, multiply that by 1,000. And if you have to convert your milliliters into liters, you divide by 1,000. Let's take a look at a practice problem. Convert 1.68 liters of water into milliliters. So if I'm going to convert liters into milliliters, that would mean I'd multiply this number by 1,000. But if we set it up with dimensional analysis, we have liters right now. We have 1.68 liters. And if I know that for every 1 liter of a solution, we have 1,000 milliliters in it, the liters cancel out. That's how I know to multiply by 1,000 and not divide. So we would just multiply by 1,000. We move the decimal place over 3 times. So 1,680. By the way, this 0 is not significant because there's no decimal place. So we have 3 significant figures right now. We still have 3. If there was a decimal place, this would count. But there's no decimal place here, so it doesn't count. So this number actually still has 3 significant figures. Now let's take a look at using molarity to convert things. If we know the molarity of a solution, we want to know how many moles there is in it, we would multiply by the molarity. If we know how many moles are in a solution and we want to know how many liters we need, we would divide by the molarity. So let's take a look at a practice problem this way. So in this question, we've got some extra information in here. We have 2 numbers. We have to figure out what's what and what do we have to do. What's the converting number is the molarity. How many moles of salt are in 458 liter container of a 4.29 molar salt water? So it's 4.29 molarity is that salt water. So we're going to convert these liters into moles. We want to know how many moles of salt are in there, so we would multiply by the molarity. If we use dimensional analysis, we would set this up because we know molarity is moles per liter, and since we know we have 4.5 liters, we want the 1 liter on the bottom to cancel out, so that's how I know multiply by 4.29. And if we try that, let's see what this looks like in the calculator. 458 times 4.29. Now take a look at this. We get this big number here. And if we take a look at this number here, we only want 3 significant figures, but it's still 1,000. So we put a 0 in here as a placeholder. This 0 is not significant. So 1,960 has actually 3 significant figures in there. I don't add the 4 because then that would make it 4 significant figures. So you know about rounding off. It just basically tells you when to round off. Here's some practice problems with molarity. Lots of different types of practice problems here. I'm trying to get you to solve for different types of things. Remember, molarity is moles per liter. So if you have the moles and you have the liters, you just divide them. Otherwise, go back to your notes and take a look at how you convert the other aspects of there. So pause the video and give these 6 practice problems a try. Let's talk about some vocabulary here and the word polar. Polar is an uneven distribution of electron density. That would mean in a molecule, if the electrons are evenly distributed around, that would be nonpolar. If one side has more electrons and the other side has less electrons, then that molecule is a polar molecule, which has a partially positive side and a partially negative side. Let's figure out if water is a polar molecule. To figure out if something is polar, we have to draw the Lewis structure, which again we talked about in our last lesson. Water is H2O, which means that there's 2 hydrogens. So we're going to have 2 hydrogens and 1 oxygen. Oxygen has 6 valence electrons and hydrogens have 1 valence electron. So we would place those out 1, 2, 3, 4, 5, 6 for the oxygen, which would mean we would have 2 lone pairs, and the hydrogens each have 1. The things that are single would get bonded pairs, so that's why we have these 2 covalent bonds here. Water has 2 covalent bonds and 2 lone pairs, and if you refer back to your notes on the last lesson, we would know that that is a bent molecule based on the shape or the angles of about 109.5 degree angles. So here is our shape of water. The red would represent the oxygen and the grays are going to represent the hydrogens. where are the electrons in water? The valence electrons are located. There's some in between these bonds, but there's some over here on that oxygen side. So where do you think the polarity of water is found? Well, the oxygen side would be slightly negative and the hydrogen side would be slightly positive. So water would have a dipole moment. The dipole moment would be partially positive in this bottom left side and partially negative in this top right side. So water has an uneven distribution of electrons. Water is polar. And because of that, because of this partially positive site where the hydrogens are and this partially negative site where the oxygen is, and the fact that oxygen is a rather small electronegative atom, it creates a strong dipole-dipole attraction between the molecules, which is a hydrogen bond. Remember, hydrogen bonds happen between things that are very, very fun. F-O-N, fluorine, oxygen, or nitrogen. When you have a hydrogen able to attract to another molecule of fluorine, oxygen, or nitrogen, you can get a hydrogen bond, which is the strongest dipole-dipole bond. Let's take a look at some properties of water now. Create a charge on a balloon by rubbing it in your hair or in a classmate's hair. You know you've got a positive charge on the balloon when your hair gets a negative charge and it will start attracting towards that balloon. Place the balloon near some running water. So it's very important you get a nice thin strip of water so that there's more surface area, so the water molecules are not a lot of water associating with each other, hydrogen bonding to each other. Get a nice thin strip of water running. What do you think will happen when the balloon is near it? When you put a positively charged balloon near water, what would happen? To test out water's behavior, I'm going to blow up a balloon and rub it on my hair until the balloon gets a positive charge. How do I know the balloon has a positive charge? Because my hair will start attracting towards the balloon. My hair is going to get a negative charge. If I put that positive charge balloon near a polar substance like water, the water's negative side should attract towards the balloon. So the water molecules will actually reorientate themselves. The oxygen side, which is negative, will attract towards that positive balloon. And the water, as it falls, will actually bend. If you try this at home and it's not bending, make sure you get the water stream to be a little thinner. Understanding the behaviors of water help us understand why water is such a good solvent. Why is it when you put solutes into water, water dissolves them so well? For instance, if you take salt, sodium chloride, and put it in water, it breaks apart. You have this white crystal, but when you put it in water, it seems to disappear, making salt water. How this happens is the water molecules will turn towards the charged ions of the salt and surround them and separate them from each other. So the sodium and chloride dissociate from each other as the water molecules surround those ions, and those ions are now floating in the water. What will happen with the sodium, the cation, is the negative side of water, which is the oxygen side, will surround that positive cation, and that will allow the cation to float around in the water. The opposite is true for the anion, the chloride. The hydrogen side of water is positively charged, which will attract towards that negative anion. You can add more and more salt and it will keep dissolving in the solution. This is called an unsaturated solution. An unsaturated solution has more water molecules available to absorb the solute. Once you start adding too much salt to the solution or too much solute to the solution, it will eventually become saturated. When it's a saturated solution, you do not have any leftover water molecules, any leftover solvent to absorb more solute. It's completely saturated. It can't hold any more. And what will happen if you keep adding the salt to the solution that's saturated? The salt crystals will actually fall and sit on the bottom. This is called a supersaturated solution. In a supersaturated solution, there's no more room in the solution to hold solute, and then it will just literally sit on the bottom. That is a supersaturated solution. in chemistry, if you wanted to make sure you had a saturated solution, the best thing to do would supersaturate it. Keep adding your solute until the solute won't dissolve anymore, and then decant the top. So leave that solid at the bottom and just take the solution, and now you have a saturated solution that can't hold anything else. Electrical conduction. Conductivity is the ability to conduct an electric current. In order to conduct electricity, the substance must have positive and negative charged particles that are free to move. An electrolyte is a substance that, when dissolved in a solvent, increases the solvent's conductivity. So having said all this, when we put something in water that turns into charged ions that breaks apart, that allows water to conduct electricity because it has positive and negative charged particles that are free to move. Water itself is a very poor conductor of electricity because it's not completely charged. It has a partially positive and partially negative side. But when you put ions in there, when you put salts that break apart into those ions, those cations and those anions, those are free to move about. A lot of movies make it look like water is this dangerous thing that can conduct electricity, and it's partially right and partially wrong. Water itself is not a good conductor, but usually wherever you see water, there's going to be things dissolved in it. Tap water has ions dissolved in it. Even rainwater has ions dissolved in it. But if you had distilled water, it wouldn't be a very good conductor of electricity. So electrolyte is also used a lot in advertising, like with Gatorade and sports drinks. Like, oh, it's got electrolytes. All that means is that it can conduct electricity. All that means is there's salt in your water. There's sugar and salt. That's all electrolytes mean. But when you use a word that the general public doesn't understand, it's a good marketing ploy because it seems to impress a lot of people that there's electrolytes in your water. It's just salt and sugar water is all that means. There are factors that can affect solubility, and the first one we're going to talk about is temperature. As temperature increases, so does solubility. What that means is, as the temperature increases, so does the amount of solute that you can get into the solution before the solution becomes supersaturated. At higher temperatures, we can get more solute into the solution before it becomes supersaturated. Let's picture this. You've got a container of supersaturated salt water. That means you've got a container and at the bottom there's some salt left over. It's completely saturated and it's supersaturated because there's some salt left over. You put it on the stove and it gets hot. As it gets hot, that salt at the bottom starts to dissolve into the solution. You don't see it anymore. So at higher temperatures, you can get more of that solute into the solution. Another factor is pressure. Now, this is about gases. I'm talking about gases. So solubility of a gas in any solvent increases as its external pressure increases. So right now, you have the weight of the atmosphere above your head actually pushing down on you. We're used to it. It's not that big of a deal. But you know when you go swimming deep in water and it starts to hurt your ears? That's because all the water on top of you is putting pressure on you. Well, we have the same thing with the gas in the atmosphere. At sea level, you have 1 atmosphere of pressure pushing down on you. So that pressure is pushing down and the gases are being pushed into a solution, into water, into the ocean. There's dissolved gas in water. That's what the fish, they use their gills to extract that gas. So let's take about an example that maybe you guys can relate to, or you should be relate to. Let's pretend we have a clear bottle of soda. We'll say it's root beer. You got a clear bottle of root beer and the cap's on there. And there is carbon dioxide dissolved in the root beer, and there's also carbon dioxide in the small air above it, but you don't see any bubbles. And that is because for every bubble that comes in or out of the solution, another bubble goes into the solution. It's a closed system. But you know it's pressurized. You know those bottles of soda or cans of soda, you know there's a lot of pressure in there. And when you open it up, it releases that pressure. And as you release the pressure, this gas is allowed to escape from the soda. And that's why we get this bubbles. We get the bubbles when we open up the container. So opening the soda Opening a soda can decreases the pressure and allows the gas to escape. So as you decrease the pressure, you're actually decreasing the solubility of the gas in the drink. This is explained by Henry's law. The decrease in solubility of carbon dioxide contained in a beverage after the cap is removed can be described by Henry's law. Henry's law states that solubility of a gas, so this is only for gases when we're talking about Henry's law, the solubility of a gas in a liquid is directly proportional to the pressure of the gas in the liquid. So how much gas you can dissolve in it is proportional to the pressure on there. So the more pressure on the solution, the more gas in the solution. The less pressure on the solution, the less gas in the solution, the more it's going to come out. So that's Henry's law. Molality. No, you're not hearing things or seeing things. This is not molarity, it's a new word, molality. Unfortunately, it almost means the same thing as molarity. It's represented with a lowercase m instead of a capital M, and it expresses moles of a solute per kilograms of a solvent. Molarity and molality have some differences, and they're very subtle, in that molarity tells you about the moles of solute per volume of the entire solution, whereas molality tells you about moles of the solute per mass of the solvent. So if we take a look at molarity here and molality up here, they both are dealing with the moles of the solute. In this case here, we got sugar water. Moles of the solute, the sugar would be the solute. So how many moles of sugar in there would be the same for calculating either molality or molarity? The difference is, with molarity, we're saying how much sugar is in this volume of the solution. Now that the sugar is dissolved into the solution, how much sugar is in the solution? That's molarity. Whereas with molality, we're talking about how much sugar is there in relationship to the solvent, to the water. So we're comparing solvent to solute when we talk about molality, but we're talking about solute and solution when we're talking about molarity. Dissociation. For stronger bonds, bond dissociation energy is higher as more energy is needed to break the bond. So dissociation is when something breaks apart. When you have sodium chloride and you put that sodium chloride in water and it breaks apart into the cation sodium and the anion chloride, that is dissociation. The stronger that attraction is, the more energy is going to be required to break those bonds. Colligative properties are properties that depend on the number of solute particles in a solution. The identity of particles is not important. If the amount of things dissolved in the solution changes a property, that is considered a colligative property. So this is all going to come together when I talked about molality, dissociation, and colligative properties in a moment. But I got one more thing to talk about before I can wrap these four ideas together, and that is something called the Van Hoff factor. The Van Hoff factor is represented with a lowercase I, and yes, doesn't have cool hair. I love how he does that. It looks like a bird shooting right out of the side of his head. You see a little bird head there? Okay, I'm getting distracted. Let's finish this up. The Van Hoff factor tells how many ions one unit of a substance will dissociate into in a solution. So Van Hoff factor talks about when you put something in solution, does it break apart? Does it stay together? And how many pieces does it break apart in? Let me give you some examples and this will make more sense. So let's talk about Van Hoff factor values. First one I'm going to do is a simple sugar. This is glucose. Glucose is completely covalently bonded together. It's carbons connected to hydrogens, connected to oxygens. But it will hydrogen bond with itself. The hydrogens of the glucose will associate with oxygens of another glucose, and they stick together, and you can actually get a solid. And so that's what sugar looks like, a solid under normal room temperature conditions. But when you put it in water, the water molecules will associate around the glucose and it'll separate that crystal into pieces. But it will only break, the glucose themselves won't break, the association between each other will break apart. So because that, if you put a glucose in water, a bunch of glucose crystal, for every glucose you put in water, you're going to have one glucose dissolved in the water. Whereas what I talked about before was sodium chloride. When you take salt in water, it dissociates into the cation sodium and the anion chloride. And so when you put one sodium molecule in water, it breaks into two pieces. So it has a Van Hoff factor of 2. I hope that makes more sense now. Things might start, at this point, start wrapping, coming together here. All right. The next one we're going to talk about is nitric acid, or hydrogen nitrate, if you will. Now, how do you know when things are going to dissociate or not? If it's ionic, it dissociates into its ions. If it's covalent, it doesn't. So if it's metals, sodium, to nonmetals, it dissociates, but if it's all nonmetals, it does not dissociate. Now this looks like it's all covalently bonded, but there's something interesting about hydrogen. Hydrogen is written on the left side of the periodic table. It's where the metals are located. Although hydrogen is not a metal, sometimes it behaves like a metal, and it can make somewhat of a ionic bond here. When hydrogen is listed as the first element, see here it's in the middle, when it's the first element, it's behaving like a cation. So the hydrogen will become positively charged, and this will break off, but the rest of it is covalently charged. So if the hydrogen is the first one, you can break it off, and then what's left over becomes an anion. So hydrogen will be a positive ion, and what's left over is a negative anion. And by the way, what this is a polyatomic anion, meaning many atoms, polyatomic. So this is called nitrate. And the whole thing together has a negative charge. So this has a dissociation factor of 2. Let's take a look at this one. This is calcium chloride. When you put calcium chloride in water, you're going to get 1 calcium, but you're going to get 2 chlorines. Those chlorines will break apart. So remember, with ionic compounds, you have the cation, which is calcium, which has a +2, and then you've got 2 chlorides associated with it. So if you put 1 calcium chloride in water, you're going to get 3 pieces, and therefore it has a Van Hoff factor of 3. So let's put these ideas together and talk about why this is important when we talk about solutions. Boiling point of elevation. When a solute is added to a solution, the boiling point of the solution increases. Many people put salt in their water when they're making pasta, as they start to boil it. And many people don't even know why. I'm going to tell you why right now. When you add salt to water, the salt breaks into the cations and the anions. And now remember, when water boils, the water molecules are breaking away from each other as a liquid and breaking off as a gas. You have to add enough energy for it to break away, and that happens at 100 degrees Celsius. When you put salt in the water, those water molecules are now associating with this positive cations and anions. Much stronger attraction to them than they do themselves with the water. And so as a result, what happens is the temperature has to be higher in order for the water to be liberated from that attraction. So when you add salt to water, you're increasing the temperature, which makes the water hotter, because you cannot get above 100 degrees Celsius for water, because as you increase the temperature, you're not increasing the temperature of the water as you're adding energy, I should say. You're not increasing the temperature of the water. What you're doing is you're phase changing the water. The water is now evaporating. So you put on the stove faster. It's not making the water hotter. It's making the water evaporate quicker. You put the salt in there, and then the water can get hotter before it starts to evaporate. So it can be over 100 degrees Celsius. Let's take a look at the formula for boiling point of elevation. The formula is delta T equals I K sub B lowercase m. And what does this mean? Delta, whenever you see a delta in science, that means change. So change in temperature. Water normally boils at 100 degrees Celsius, so this is the change in temperature, how much hotter it's going to get, times I, which is the Van Hoff factor, which you put in there, how many pieces does it break into? The constant is B, would be the constant boiling point for the solvent. So water would have a different constant than, say, ethanol, if you're using ethanol as the constant. So these are constants, they don't change. And M is molality. That's why we talked about molality. And that's basically how much did you put in there. So let's take the example of salt. The Van Hoff factor for salt would be 2, which if we put sugar in there, it would only be 1. So that doubles the change in temperature for the amount that you put in there. The constant for water would be the same, and the more salt you put in there, the greater the change in boiling point. Now, this also works with freezing points. Freezing point of depression. When a solute is added to a solution, the freezing point of the solution decreases. So again, if you put salt in water, those ions, the water is going to be attracted to those ions, and it's going to make it harder for the liquid to become a solid. So it'll have to be colder and colder and colder for it to become a solid. So it lowers the freezing point when you add a salt in there. And the equation looks very much like the equation for boiling point. It's the change in temperature is equal to the Van Hoff factor of what you put in there times the constant, but this time it's the freezing point constant at the constant that water freezes times the molality of what you put in there. Let's take a look at this and think about an application for it. When it snows and there's ice on the ground, we put magnesium chloride. Do you say salting the roads, salting the sidewalks? It's actually not sodium chloride. It's magnesium chloride, or mag chloride they sometimes call it. Magnesium chloride's formula is MgCl2. Magnesium's got a charge of 2 positive and chlorine's negative 1, so you need to have 2 chlorines to offset the magnesium. We generally don't use table salt. Why is that? Well, if we understand this formula, the answer comes out to us. Why? Well, for the same amount, the same molality, it's the same constant, but the Van Hoff factor is different. Magnesium chloride has a Van Hoff factor of 3, which would change the temperature at which water freezes greater than if you use sodium chloride, which has a Van Hoff factor of 2. So that's why we use magnesium chloride for the sidewalks and stuff like that. And it makes it so that water will freeze at a lower temperature. So when you put that on the ice, what will happen is the ice will start associating, the water molecules in the ice will start associating with the salt and break out of the solid that it's in and turn into a liquid. That's how it works, guys. Okay, I would like you to listen to this question with me and pause the video and try to answer it on your own. What would increase the boiling point of water more? The same amount of sugar or table salt added to it, and why? So pause the video and give that a try. What would increase the boiling point of water more? The same amount of sugar or table salt, and why? Do yourself a favor and pause it and give it a try. And hopefully you did that. So let's go over what I would be looking for a correct answer to that. There's 2 things I would be looking for. The correct answer should have 2 points. First, you should say that table salt is NaCl, would have a boiling point, would increase the boiling point more than sugar because it dissociates, that's one of the key vocabulary words we talked about, twice. It turns into sodium and chloride. So it has a Van Hoff factor of 2. And the sugar would dissolve in water but not break up into multiple pieces. The sugar would stay together as one piece, so it would have a Van Hoff factor of 1. But that's not enough to answer the question. We have to elaborate, how does that affect with water? You gotta take it that next step to show that you understand. The water creates stronger bonds to the dissolved substances, making it harder to phase change from a liquid to a gas. Since salt dissociates into twice as many parts, it will require more energy to boil the water. There's going to be more water molecules attached to something else. It's going to have more colligative properties in there. So hopefully that makes sense. Last but not least, here is another set of practice problems that I'd like you to give a shot to. First one is write the Van Hoff factor for the following. So I've got some additional compounds here, and I would like you to write the Van Hoff factor for these different compounds. So how many pieces do they associate with? Remember, if it's an ionic compound, it breaks apart. If it's got covalent bonds, they don't break apart. So look for those metals and break off the metals and whatever's left over and try to figure out what those charges are. Number 2, of the 5 compounds listed in question 1, which would have the highest boiling point of elevation when added to water? So using the same quantities of all of these, which one would have the highest boiling point? and make sure you understand why. And then of the 5 compounds listed in question 1, which would have the warmest freezing point of depression? In other words, it doesn't freeze as much. So pay attention. The wording could be a little bit tricky. Of the 5 compounds listed in question 1, which would have the warmest freezing point of depression? Meaning it doesn't depress as much. It's the worst one at lowering the freezing point. So give those a try. Contact me if you have any questions, you want to go over your answers to this, and good luck.